Welcome the grade 11s. This is Mr. Ndabezeta, and then we are on section F. We will be looking at relations and functions. In the introduction, we read in grade 10, you dealt with the graph of the linear function, which is a straight line where the gradient remains the same. The rise and run leads you to exactly the same direction at different points. The hyperbolic function, the hyperbola, and you also dealt with the quadratic function, which is the parabola, and the exponential function. I think that we are going to explore all these functions. We will look at the straight line, the hyperbolic function, the quadratic function, and so on, and the exponential function. So 4 types of graphs we will look at in grade 11: straight line, hyperbola, parabola, and exponential. This year, we are going to extend our knowledge of these functions by further studying their horizontal translation. Okay, translation meaning moving a graph either up or down, left and right. This is to translate, to move from one place to another. So meaning we can say translation or displacement. The definitions, the equations in the standard form. Since y is obtained from x, in essence y is dependent on x. So y is the dependent variable, x is the independent variable. The equation in standard form, y on its own is the most commonly used form of any relation. So we are saying y is always equals to something as a function of x, or we can say y equals maybe 2x plus 1. So y is a function of x being the independent variable, and y being the dependent variable. So there are unique features of these relations and functions. For each of these relations, there are unique, hence most important features. And these are what determine the basic shape of the graph. So these unique features, some of them determines the basic shape of a function. Now let us try to look at the translations. You will discover that many sketches have exactly the same shape but are in different positions relative to the axis being the y or the x. These shifts are known as translations. This is fine. So we are translating the graph maybe up or down, left and right, relative to the x or to the y ordinate system. And then x and y intercepts. These positions are the graphs on the coordinate axis in the Cartesian plane. So this is the role that the x and y intercepts play. They positions the graphs on the coordinate system, which is the Cartesian plane. The x-intercept is always determined by letting y be 0. The y-intercept is always determined by letting x be 0. And then we have the axis of symmetry. An axis of symmetry is a line which intersects a graph so that one side of the graph is mirrored on the other side. So, okay, the axis of symmetry is a line, first of all, which intersects a graph so that one side of the graph is mirrored on the other side. Symmetry is often used to easily determine the values that have not been given. So you can have one side of a graph where the values are provided, and you want to find the values of the other side which are not given. So you can draw up a line which is called the axis of symmetry, which mirrors one piece to the other side of the graph so that you can find the coordinates or the values of that which is not given. Okay. And then we have the asymptotes. This is a line that the graph approaches but never reaches. So a line can try to approach the graph or even the line. The graph can try to approach this line, but it never really get there. It will approach this line, but it will never get exactly at that line, and we call this the asymptote. So the asymptote is a line that the graph approaches but never reaches. And then we have the domains and the range. The domain is a set of all the possible independent variables, because we said that x is the independent and y is the dependent. Hence they are saying that the domain is a set of all the possible independent variables. In essence, first x coordinates of a relation. The range is a set of all possible dependent variables. In essence, the second, which is the y coordinates of a relation. Now remember, a relation is a function. A relation is a function, or is a relationship where one value of x is mapped to exactly one value of y. But we will talk about these relations when we get time. One to one, one to many, many to one, and many to many relations. We will try and look into this. These are the first chapters that are dealt with when you study engineering mathematics. We will look into that. We will look into that. Right. Now that we have a brief summary of what we will be looking at, let's now go and try to define the linear function. And we will be revising this because it has already been dealt with in your grade 10. The following is a summary of to remind you of what you have covered with respect to the straight line graph. Now the equation in the general form is given as follows. So where do we go now? Let me just try to position my things very well so that we may continue in this. All right. They say that the following is a summary to remind you of what you have covered with respect to the straight line graph. So we know that the general equation of a straight line, it's in the form ax plus by plus c is equals to 0. Let me just draw up a line here. So this would be the general form of a straight line. So this would be ax plus by plus c is equals to 0, the general form. And we also have the standard form, which is y equals mx plus c, or even y minus y1 equals m into x minus x1. So there are three ways in which we can represent a straight line. There are basically three ways. Okay, let me just zoom in. Very good. So this is what we have. We have the general form, and we have the standard form of writing a straight line. Okay, and the most important feature of the straight line is the gradient, and this gradient, which is m, equals a change in y over a change in x. So a change would mean that you have the final minus the initial, x final minus x initial. That would mean the change, which is how many times you rise as you run. Okay, this is fine. So we are using m to denote that this is the gradient, which is the change in y over the change in x. So meaning you must have the coordinates, which are the initial point where you began, and the coordinates of the final destination where you ended. And we will name those coordinates as x1, y1 for every coordinate there is an x and a y, And the second coordinate, we can say x final and y final. This is what we can conclude. Okay, so in a straight line, the gradient determines the basic shape of a graph. So the gradient gives us the basic shape of a graph. This is the function of the gradient. Okay, the gradient indicates the way in which a point moves on a straight line. So the gradient also indicates the way in which a point moves on the straight line. So it tells the point whether you will move in this way, whether you will move in that way. Okay, so if the gradient gives the basic shape of the graph and also indicates the way in which a coordinate will move on the graph, that is fine. That is fine, we understand that. But examples are always there to give us more insight into this. So the straight line is a constant rate of change. So the rate of change remains constant, not the same, it's constant. And how do we show that? Now, if the gradient is positive, it will have this shape. This is the shape, and the shape indicates the way in which the point will move on the straight line. This is how the point will move on the straight line. And when I find the gradient, it tells me the basic shape of the graph. Okay, and if the gradient is positive, this is the shape of the graph. Whereas if the gradient is negative, this is the basic shape of the graph. And the coordinates will align themselves in the basic shape of the graph. All right, and there is a constant rate of change as we are running and rising on that line, and the rate of change remains constant. All right, and when the gradient is 0, we have a horizontal line, and the coordinates will align themselves with that line where the rate of change remains constant. Okay, and if the gradient, you have a vertical line where the rate of change is also constant, but here the gradient is undefined. The gradient is undefined here. So this is not a function. Why is this not a function? If, for example, I draw up a Cartesian plane, x and y, and I draw up a straight line with the coordinates there, I can see that what is happening here, for the same value of x, I have different values of y. So x is mapped to more than one value of y. and this is not a function. Hence we are saying the gradient is undefined. But we will talk about this some other time, where we look specifically into this and see why we are therefore saying that this is not a function. But for now, you should just know that for the same value of x, we have different values of y, and therefore this is not a function. Okay, all right. Now let us try to look at the vertical translation of the graph y equals mx plus q. We are trying to write this in a standard form. And when we are here, we will try to say, okay, this value that we are adding to the coefficient of x, which is the gradient, it's what we call the translation. So the value added to the basic graph is its vertical translation. So this is a translation that translates the graph vertically, so meaning up or down. Okay, so meaning if I have a gradient that is positive, and if I draw up a Cartesian plane, I know that if the gradient is positive, this is what I will have. Okay, and remember, this q is our vertical translation. It's the value of y, and here the value of q is positive because y is positive in here. Okay, and in here the value of q is 0 because x and y is 0 there. And in here the value of q is negative because y, it's negative in there. Okay, now this is the translation that the function had been able to undergo, and we understand that. We fully understand that the graph can be translated up, and it can be on the upper x-axis if q, the value of y, is positive. It can be exactly at the beginning if the value of q, the value of y, is 0, and it can be below the x-axis if the value of q, the value of y, is negative. So these are the set of translation that the straight line graph had been able to undergo. Okay, for the value of m that is positive. And we can also investigate for the value of m that is negative. We know that we will have this basic shape, and q here is a positive, and q here is equals to 0, and q here is negative. We understand that. There is no problem with that. All right. Be that as it may, we can continue in this, and we can look when the gradient is equals to 0, whether there are any transformations that the function will undergo. We know if the gradient is 0, the straight line graph, it's still a function. Why? Because for every y value, for every x value, can you see this? The value of y remains the same. For every x value, the value of y remains the same. So this is a function. So meaning for different values of x, it's fine if we have the same value of y. That is a function. But for the same value of x, we cannot have different values of y. This is what we talked about, where we said the gradient is undefined. Why? Because for the same value of x, we have different values of y. That's not a function. But it is a function if for different values of x, we can have the same value of y. So here q, it's positive, greater than 0. We can see that. Okay, that is fine. And here q is equals to 0 if we are exactly on the x-axis, and in here q is less than 0 because y it's negative in there. And we know that for a horizontal gradient, the gradient is always 0. If you have a straight line function that is horizontal, you know that the gradient is 0. And we're going to prove that when we deal with the calculations. Okay. Now let us try to look at the intercepts with the axis. Irrespective of the graph that is being drawn, the intercepts are always found as follows. For the y-intercept, always make x 0, and for x-intercept, always make y 0. Okay. Now, how do we draw up the straight line graph? Remembering the importance of the shape as well as the position of the axis, the following is needed to draw the graph of a function. The equation in the form y equals mx plus q, which is the standard form. The vertical translation is required. The y-intercept by letting x be 0, the x-intercept letting y be 0. The gradient, which is the coefficient of x when the equation is in the standard form. So these are the things that are needed for us to be able to draw up a straight line function. So meaning in the second tutorial, we will be looking and dealing with that.